What I'm going to talk about is really just telescopes to receive information from space. And here it is. So what you see on this first slide already is how telescopes are changing. You look at the upper right, that's a telescope that you think you recognize. It has a round dome, it has some structure in it, it has a mirror in it, as you will see. You see at the bottom, you don't see at the bottom, unfortunately, there is a set of antennas. That's another type of telescope. It's a radio telescope that we use and people use already. And then on the left side, that is a radio telescope as well. So there, we move away from dishes. We move into what's called phased arrays. So we use different physics to actually build up new telescopes and new ways to observe the universe. So these are pictures all taken from the ground. So these are not HST pictures, but they're comparable to HST pictures or to the Hubble Space Telescope pictures. Admittedly, most of these objects are bigger, so we don't need as much resolution as the Hubble Space Telescope provides, but they are comparable. And this is one of the reasons we do astronomy. It's to understand the past of the universe, and by understanding the past of the universe, to be able to look into the future, what this universe will be. But it's also the beauty of what the universe has to offer to us. The many different objects, being stars being formed, or stars that die in explosions and things like that. One thing that we need to understand is that when we observe the sky, we are looking through windows. Okay? Our atmosphere has a very important function. It's actually protecting us from radiation from out of the sky, solar radiation in terms of UV radiations and things like that. So you see here a graph that shows you how the atmosphere, how the photons come through the atmosphere. This is electromagnetic radiation, and you see that there are these windows. Let me see. Well, I can't do this. Over on the left side, you see the radio telescopes. That's the radio place. That's the reason you actually can listen to your radio in your car, because as Hertz discovered, the electromagnetic waves can travel in the atmosphere. Whereas if you go into the X-ray range, you will not see the sky. If you would build an X-ray telescope on the ground, you would not see the sky, because the atmosphere is shielding all the light that's coming in that wavelength range at that energy. And so you see the combination from ground-based astronomy, where you can do things from the ground in the radio and in the optical, and things where you have to go into space. If you want to do X-ray astronomy, you have to do this from above the atmosphere. That's why we need satellites to do this. There is an interesting moment in history right now, in astronomical history if you want, which is that right now at this moment, we can essentially observe the whole electromagnetic spectrum that the sky has to offer to us. This will disappear in a few years when the X-ray satellites that are currently flying are going to run out of fuel. We have some of the millimeter telescopes, satellites, they will run out of fuel pretty soon, and so we can't observe those. Now, what's happening right now is sort of a revolution that will come in the next few years, which is we will observe the sky with particles that are not photons, not electromagnetic radiation, but there will be other messengers that will tell us about the sky. And these messengers are particles like neutrinos. We measure the neutrino flux from the sun. That has been done for many decades. There is one other astronomical object that has ever been seen in neutrinos, which is a supernova explosion 180,000 light years away. And we will be able in the future to see gravitational waves and also to directly detect dark matter. These are all physical problems that we need to target to understand the universe a bit better. You need different telescopes for these. The neutrino telescopes are all underground. They're not above ground, they're underground, and they actually would like to see the neutrinos as they come up from the Earth, if you want, from the other side of the Earth, because the neutrinos interact very little. Jeffrey mentioned this. The universe, we've learned in the last 2 decades that the universe is made up of much more than what we know. you've seen, Jeffrey Hoffman showed you this picture of the Hubble Deep Field with all these galaxies in there. What we see in there is 4% of what the universe is made of. Okay? This is this little wedge, it says here 5%, 45% is what we know is what we call baryonic matter. And the rest, the remaining 95%, is made up of things that we have observed indirectly. We know about them, but we don't know what they are. The physicists are trying to understand what this is. This is all coming out of astronomy right now, and this is one of the topics that we need to solve in the next 15 to 20 years. Here's another example of something that Jeffrey already mentioned. This is the planets around other stars. He showed you many pictures about the planets around the sun in our solar system, but what you see here, this is one example. The top figure is one example. This tiny little dot that you see next to the black dot in the center, the black center here is the light from the star is blocked out. Okay, there's a little device that just blocks the light from the star, and you see towards 10, 11 o'clock, there's a little white dot. That is a planet that's orbiting this star. The amazing thing is this planet is orbiting this star within this, what looks like flames is a large disk of dust that's orbiting that star as well. Okay, so this is a planet within a disk, which is a completely different environment from what we know in our solar system. So this is another example of how we're going to explore the new worlds with these planets, these exoplanets. Jeffrey already mentioned there is now billions of planets. We think we know billions of planets. Now, what he didn't tell you is we know about these planets, but we actually can't take direct images of them. This is one of the 3 examples that we know, okay? Everything else, we know about the planets that they're there, but we can't actually directly see them. And so one of the things in the future that we need to do is we need to build telescopes that we can investigate these planets and possibly find life on them, or find signatures of life on them. So here's an example. This is unfortunately not working. Let me see if that works. No, so unfortunately this was supposed to be 2 small movies. What you see here is the very center of our own Milky Way. And what you see is these dots here are all stars. Now, if I could show you the movie, you would see that these stars are actually moving on the sky. We now are able to observe how these stars move. It takes about 20 years to observe those things. So you have to come back every year and take another image. So your film camera is a very, very slow film camera. It's a telescope in this case. And if you then take this long enough, you see that these points are actually orbiting. They're going around a dark spot where there is nothing. And that dark spot where there is nothing is the black hole that holds this galaxy together. Okay, so at the center of our own Milky Way, there's a black hole that's extremely massive, 4 million times the mass of our own sun. Okay, squeezed together on a tiny little thing. And that's what you can see there. What we can do with the next generation of telescopes is we can actually measure whether Albert Einstein was right. Okay, we can measure whether his theory of general relativity is the correct one for very strong gravitational fields. So this is another movie that doesn't work either. This actually has, well, it's very hard to see. There was a counter at the bottom, and it actually counts up to 2043. So I could have shown you the future for the thing. What this movie would show you is a gas cloud that was discovered last year that's actually falling into the black hole. That will give us a chance to observe how a black hole eats up material. So that will be a first to see. By the way, here's the observatory on the upper right that Anton Zeiling has been using. That's the observatory that was sending the signal, I believe. And is that right? Yes. And then there is a solar telescope on El Teide in the middle, which is amongst those telescopes that actually receive the signal. So this is a current set of observatories that we're using. Again, you see different shapes. This down here in the lower right, this is actually a field that's laid out with diodes to measure radiation coming from the sky. These observatories become very, very big. Let me give you an example here. This is an observatory that we are using. It has, you see on the lower left, 4 telescope domes. Each of those domes has an 8-meter telescope inside. An 8-meter I mean is the size of the primary mirror. Okay, so it's 8 meters in diameter. It's over 50 square meters surface. As a student once said to me, this is bigger than my apartment. Okay, so we now have telescopes that are the size of a one-room apartment, admittedly, but nevertheless. So you see on the left we have 4 of those. We have, in addition to those, smaller movable telescopes of 1.8 meter size. And then on the right you see the Milky Way going across. You see the two close neighboring galaxies to ours, the Magellanic Clouds in the south. And you see that this telescope is actually shooting a laser into the sky. What we do is we use this laser to create an artificial star in the sky to help us observe, because we have to deal with the atmosphere. I wanted to show you here something that often gets forgotten. We look at the sky with our own eyes, with what we see in what's called the optical. We're now building, together with the Americans and East Asia, we're building a telescope which is composed of 66 individual antennas. And we can actually move these antennas so that we can refocus, if you want, the telescope. And it's operating in a place where we can't really see it with our own eyes. It's in the millimeter and sub-millimeter range. And let me just demonstrate to you what this does. What you see here is a picture in the optical. This is a picture in the blue light, and you see the stars. Now, each of these stars has temperatures of a few thousand degrees Celsius. Okay? So that's the surface. Our sun has 5,000 degrees Celsius on the surface. Yes. So you see this dark cloud in there. That dark cloud is dust that's blocking the light coming from behind, blocking the lights of the stars behind this cloud. So we can't see those stars. Now, if you take that same observation in the infrared, this is now radiation that we can feel as heat. Okay? If you take that observation, you already see that you see more stars. Some of the stars come through. Now, if you would be able to observe this in the millimeters, at millimeter wavelengths, okay, it's going to look like that. Now, that cold dust that you couldn't see before is glowing because you can now see the cold universe, which we can't see with our own optical eyes. Okay, all the stars have disappeared. They're too hot to be visible, but the cold gas, the cold dust, is visible now. Now, just to give you an example here, this is how I look like in infrared radiation. Okay, and you look at the glasses. The glasses are much, much colder, which I never realized. They're much colder than my face. Okay, so that's what we're doing with those new telescopes. This is how we're building this. This is being constructed right now. We're going to be finished next year. You need these transporters. Each antenna is 120 tons. You have to pick it up. You have to put it down to a millimeter accuracy at 5,000 meters altitude. You see at the bottom how they are built. This is done in Chile. Now the next step, I have 3 more slides. The next step is the next giants. Okay, we want to build telescopes that are bigger than what we have right now. And so we want to build these. On the left side you see a picture, a dream, if you want, of a telescope that has 40 meters in diameters. Okay, 40 meters from one edge of the mirror to the other edge of the mirror. This is about twice the size of this room, just to think about this. Okay, now you pick this up and you point it every place in the sky. So that's the daunting task that we're looking at. We need this to look at these planets that are being discovered by these various satellites. On the right, you see two other models. This is two American projects. One is called the 30-meter telescope, so that will be a 30-meter diameter telescope. And the other one is called the Giant Magellan Telescope, which is a slightly less, slightly smaller, but also a big thing. Just to come back to my one-room apartment, the 50 square meters, this thing, the 40-meter telescope, you can build your house on that mirror if we would let you, but we will not. So this is the inside. I'm going to skip this mostly. We have essentially received from our countries in ESO the go-ahead. So we have the project is ready. What we can do now is we can actually start building it. So it's provisionally approved. Here's another example of one of the giants of the future. This is called the Square Kilometer Array. This is a radio telescope. That telescope will have, as the name says, it will have a collecting area of 1 square kilometer. Okay? That's the idea, to have thousands of antennas spread around. As a matter of fact, this should cover half of Africa, okay? Because you need that big size to see very accurate in the sky. And then to come back to the last one, this is now a trial. Actually, it's working, but it's not working at this scale, to see cosmic rays. Okay. What happens is when a cosmic ray hits the top of the atmosphere, it creates what's called Cherenkov radiation. It creates secondary radiation, which you can observe with big telescopes, big optical telescopes. And that's happening right now. I've mentioned the neutrinos down there. The neutrino telescopes are working. They need to become bigger, and they need to become more sensitive so that we actually can then explore all the phases in this universe that we see. So I'll finish with this one. It turns out ESO, the organization I work for, is turning 50 years this year, so we're celebrating with our very large telescope. And so hopefully this is going to last for a bit. Thank you very much.